Hello, Mr. Holmes with another Zero to Hero video. In this video we're going to lay the foundation for number representation, and if you recall, everything inside the computer is represented in binary because electronic circuits make use of a microscopic little switch called a transistor that can be set either to a 0 or 1. So the question now is, how on earth do we represent numbers using only switches that I can turn on or off? We represent the state of the switch being off by a 0 and the state of the switch being on by a 1. I'm going to develop the idea of how binary representation actually works in something which is commonly known as a grid. And in this grid, we are using 4 bits, 4 binary digits. Each binary number can only be representing the digits 0 and 1, compared to the decimal number system, also known as the denary number system, which is base 10. Now, our number system, the decimal denary number system, has 10 digits, and they are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so, when we get to the 9th digit, what we do is we roll over, and we then turn from a single digit number into a 2-digit number. Add another column if you like, and hence we get 10, 11, 12, and so on. And then we then roll things over, and the units go from a 9 back to a 0, and we carry a 1 over into the tens column, and so the 1 in the tens column rolls over and becomes 2. The process continues. So if we were at 99, if I add 1 onto that, we know the answer is 100, but let's think about what that means. It means I've rolled the 9 back to a 0, I've rolled that 9 back to 0, and I've carried a 1 over now into the third column, so now I have a 3-digit number. Positional values in a number system should not be anything new to you. We've got to try and figure out how do we do this when instead of using zeros and ones. I'm going to use this grey grid. So this, if you like, is going to be my unit column. This is going to be my tens column for binary. It's not worth 10. We'll get to what it's worth in a minute. This is going to be my third column for binary, and finally my fourth column for binary. We start with the obvious thing, namely that how would I represent 0 in binary? Well, obviously I'd turn that little switch of that binary digit off, and I could turn the binary digit, the bit, on to represent a 1. So to get to 2, I would do exactly the same principle that I did here. When I run out of my digits in decimal, I simply put a 0 in the column I'm in, and I carry a 1 over to the next column, a 2-digit binary number. And hence, that's the binary value for 3. And so we can continue to roll this on. The binary numbers up to 7. Now, I want to represent these as 4-bit binary numbers, so what I'm going to do is I'm going to pad the left-hand side of my table with zeros. I haven't changed the meaning of anything, I've just made sure that I have placeholders in those columns so I don't get confused. And I can continue this all the way along. Simply by copying and pasting this pattern over, I can actually generate the numbers 8 to 15. Instead of having a 0 here in the fourth column, replaced the zeros in the fourth column by 1s for the numbers 8 to 15. Now, there are patterns everywhere here. Let's have a look at some of those patterns. As I go down the unit column, we continuously switch between zeros and ones as we go down the columns. Now, in the first column, we have 1 0 and 1 1, and then that pattern just continues all the way down. For the second column, is that the run or the size changes from 1 0 to 2 zeros, 2 1, 2 zeros, 2 1s. Column 3, the run size simply doubles from 2 to 4. I then write down 4 zeros, 4 1s, 4 zeros, 4 1s, and finally in column 4 we have 8 zeros followed by 8 1s. Using this technique, it's really easy to draw up this table, but this table doesn't stop giving yet. If we look at the powers of 2, which are 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, and 2 to the power of 3 is 8, it gives us the very special numbers 1, 2, 4, and 8. So those are my powers of 2. If I look at the decimal representation, the decimal values for 1, 2, 4, and 8, and I compare them to their binary representations, you'll notice on each of those rows that there's only a single 1 in any one of the columns. For 1, there's a single 1 in column 1. For the 2, there's a single 1 in the column 2. For 4, there's a single 1 in column 3. And for the 8, there's a single 1 in column 4. And this in turn actually tells us what value each of these columns in fact has. So the first column has a decimal value of a 1. Everything in the second column has an equivalent value of a 2. Everything in my third column has the equivalent decimal value of 4. And everything in the fourth column has the decimal equivalent value of 8. This is very easy to do. That column, like my units, in decimal, has the value of 1. But instead of my second column having the value of 10, it has the value of 2. I simply double. 2 doubled is 4, and 2 doubled gives me 8. And I can repeat that labeling. Remember how I'm getting these numbers? I start at 1, and I just keep doubling as I go from right to left. This then gives us a very simple technique for turning decimal numbers into binary numbers and vice versa, called the grid. If I want to go from a decimal number to a binary number, I've got to fit it into one of these perfect powers of 2. We'll do an example in a moment. If I want to go the other way around, I simply have to look up what column I'm in and multiply, if I have a 1 in that column, by 2 to that power number. So for instance, if I go to 11, let's check that this works. There's 11. I have a 1 in the 8 column. So 8 plus 2 gives me 10 plus 1 is 11. There we go. Right, so we're going to look at an example now of converting 81 into an 8-bit binary number. And what I've done is I've simply created and labeled up a grid. Very easy to do. The first column has a place value of 1. I double 1 to get 2. Double 2 gives me 4. Double 4 gives me 8. Doubled gives me 16. That double gives me 32. That double gives me 64. And that double gives me 128. Those are my 8 columns. So what I need to do, these represent the perfect powers of 2. What I have to do is I have to fit 81 into these perfect powers of 2. 81 is too small for 128. So I can't use 128, but I can use the 64. Put a 1 in the 64 column, and all I need to do now is subtract 64 from 81, and that gives me what's left over. And the answer is 17. I can't use the 32, but I can use 16. If I take 16 away from 17, that gives me the magic power of 2 of 1. So I put a 1 in the 16 column and a 1 in the 1 column. Everything else gets a 0, and there we have it, ladies and gentlemen, the binary representation for 81 using the grid method. Very easily worked out. The only thing that remains to do is to write down the answer in the correct fashion. I can write down 81 is equal to, reading from left to right, be 0, 1, 0, 1. I'm going to put a space because I want to group it in nibbles. It's easier to read. And 0001. Now I can't write that down like that. What I need to do is put a little 2 behind it, or a little subscript 2, so that I'm very clear about the fact that this is a binary number, so base 2. Alright, that concludes the calculation of a decimal number into a binary number. We're now going to look at the reverse process, namely converting a binary number back into its equivalent as a decimal number. Okay, this is equally simple. Now just use the grid again. All I have to do is fill in my 1s and 0s into the grid. So I put that into the binary grid. And all I now need to do is I simply begin expanding it. Right, so I have 128, because I have a 1 in the 128 column. I then have 16. I then have 8. I have a 4. And I finally have a 1. Going to be a bit smart about this. I can pair the 16 and the 4 together to give me a 20. 148. 8 and 1 gives me the 9. And so I just going to have to add 9 onto that, which gives me 157. As my answer is 157 in decimal. And that concludes the introduction to binary and decimal number representation. In the next video we'll look at using the grid to do hexadecimal and to convert between decimal hexadecimal. Thanks for watching. Mr. Holmes signing out.